All right, so this is 8.3. Hopefully the notes go well today. It's a work in progress, and we're trying to make steps as we go. So section 8.3 today is called rational functions. And as it says, let me get my pen out. I'm a little behind, sorry. A rational function is a function written as this. F of x equals p of x over q of x. A lot of x's in there. F of x equals p of x over q of x. And I guess we should say where p of x and q of x are polynomials. What is a polynomial again? So it's been a little while. Back in chapter 5, we talked a lot about those, right? Polynomials, remember, many terms is kind of what that word polynomial actually means. It can be a variety of things. So we said like monomials are like one term, so maybe like 4x. Could be a binomial, two terms, like x minus 3. You could have different degrees, so like 3x squared minus 5x plus 7. This is a trinomial with degree 2. We can go on from there, right? 5x to the 4th minus 7x cubed plus 12x minus 5, so on and so forth, right? So those are polynomials. And so what this means is for a rational function, it's basically one polynomial divided by another. And when we think about division, there's something we have to account for. I don't know if you guys remember this, but back before spring break, we talked about when we're looking at division, the denominator of a function cannot equal 0. So down here where it talks about domain, our emphasis is going to be on the denominator. So in this case, that would be q of x. That is in the denominator of our function, so that q of x, remember it's a polynomial, that q of x, whatever it is, can't equal 0. Now, q of x could take different shapes, right? We said polynomials can be all kinds of different things. It could just be a single term. It could be a whole bunch of terms. So whatever's in the denominator cannot equal 0. For instance, let's say if you have something like this. So I'll do a couple small examples here. Let's go ahead and write these in. Let's say you've got f of x equals 2x over x minus 3. So again, our focus is on the denominator. The denominator here is the polynomial x minus 3. We do not want that to equal 0. So for this, our domain is all real numbers not equal to 3. Or x not equal to 3, right? Sometimes we look at that either way. Okay. Let's say you got something a little more complex though. Let's say, let me give you another quick example. You've got f of x equals, let's say you've got 3x squared on top. Let's say on bottom you've got 2x plus 8. So go ahead and write that in. F of x equals 3x squared over 2x plus 8. Now, we don't want the denominator to equal 0, so when does 2x plus 8 equal 0? One thing I would do here, and one thing it's good to get in the habit of, is always looking to factor. As you start to deal with polynomials of larger degree and more terms, if you get down to some of these, factoring is going to be useful here. So in this case, the denominator, again, that's all we're focused on, 2x plus 8, you can factor out a 2, right? Make it 2 times x plus 4. What that allows us to do is it allows us to see that, okay, x plus 4 is really where my focus is. So that means when x is negative 4, that's when I'm going to get 0 in the denominator, right? Because negative 4 plus 4 would be 0. 0 times 2 is 0. So x can't equal negative 4. And again, factoring is our friend. That was helpful here. Okay? Let's go down. In this example here, there's 3 different graphs. And then actually each of these graphs matches up with these little paragraphs here as descriptions. let's take a look at what these graphs are. They're all rational functions. They're all polynomial over polynomial. But they all represent different things, or sorry, different types of what we call discontinuity. And discontinuity is a thing you're going to work with a lot here, and then as you keep going in math, pre-calc, and all that kind of thing. Discontinuity, we can go ahead and write this in, because you're going to see this term a lot. Discontinuity, D-I-S-C-O-N-T-I-N-U-I-T-Y. It's simply a point on the graph, where the graph is not continuous. So that's really what discontinuity means. Discontinuous, right? Now back up at these three graphs we have here. These are three different examples of this, okay? Looking at just the first graph here, this is an example of a what's called continuous function, okay? And it's continuous because there is no point of discontinuity. It's continuous. You can keep your pencil on the paper and you can draw the whole graph without having to lift it up, okay? Kind of a simple definition. Now, this first paragraph here kind of explains why it's continuous, and that has to do with the rational function that it matches with. So let's go ahead and read it together. For the first rational function, y equals x squared over x squared plus 1, there is no value of x that makes the denominator 0. Again, that's our emphasis here, guys. When is the denominator 0? In this case, there are no values for that. This graph is a continuous graph because it has no jumps, breaks, or holes. You can draw the graph in your pencil and it never leaves the paper. So like I said, the key thing here that I underlined, when is the denominator 0? Looking back up at that equation, y equals x squared over x squared plus 1. If we're focusing in on that denominator, x squared plus 1 equals 0. And if you tried to solve for x there, you would get x squared equals -1, x equals square root -1. That we know is an imaginary number, which means we have no real solutions here, which is why this is continuous. Okay? The second one, second graph and second equation. Okay, let's look at the second paragraph here. It explains that one. Let's go ahead and read it. The graph of y equals x plus 3 times x plus 2 over x plus 2 has a removable discontinuity. Okay, that's a key word there, removable discontinuity at x equals -2. The hole in the graph is called a removable discontinuity because you can make the function continuous by redefining it at x equals -2 so that f of -2 equals 1. Here's what you need to focus on. With this second graph and second equation, this is removable discontinuity. And what that looks like on a graph is a line, but it's got a hole in it. Okay, so if you were to even graph this on your calculator, it would graph, but then it would jump over the spot where it's discontinuous, and it would keep going. You get these kind of discontinuities, you get removable discontinuity when your equation has something in the denominator, but that also cancels with something on top. So here's what I mean. If we look at the function here, y equals x plus 3 times x plus 2 over x plus 2, we always focus on the denominator, right? When does x plus 2 equal 0? Well, that's pretty easy. When x is -2, right? And that's where our discontinuity comes into play. That's where this hole in the graph is. But if you look back at the equation, y equals x plus 3 times x plus 2 over x plus 2, that x plus 2 on bottom can cancel with an x plus 2 on top. So we don't just get rid of it altogether. We still account for it. And that's what that hole in the graph is all about, okay? That's why it's a removable discontinuity. Maybe if it helps you remember, you can kind of remove these two things from the equation, right? You can remove the two pieces from the equation by kind of canceling them. So maybe that's how you can kind of link removable discontinuity, remove them from the equation. Maybe not. The third graph. We've seen graphs like this from 8.1, right? This kind of looks like inverse variation. Let's go ahead and read about that in the third paragraph. it says the graph of y equals x plus 4 over x minus 2 has a non-removable discontinuity at x equals 2. There is no way to redefine the function to make the function continuous. So this is non-removable discontinuity. Non-removable discontinuity. And that's what, and when you have that, you get an asymptote. So removable discontinuity just had a hole in the graph. Non-removable discontinuity gives you asymptotes. And you can see those drawn in there with that dotted line on your page. Okay? The asymptote is going to be whatever is in the denominator, right? So again, focus on the denominator. Your denominator here is x minus 2, which means your asymptote will be at x equals 2, right? Because when x is 2, that would be a domain restriction. If x is 2, you're going to get 0 in the denominator. That's where your asymptote is going to lie. Okay? All right, so continuous, removable discontinuity, non-removable discontinuity. Let's go to the next page. Point of discontinuity, we already kind of talked about that. That's just the point where the graph is not continuous anymore. And again, when we're looking for this, we must think denominator. So I guess I can say it's the point where the graph is not continuous. Always thinking denominator. Last thing here, we have a few examples.